Hello there, ladies and gentlemen. I hope you're all doing well. Thanks for joining me as we take a look at question number 3 on the 2017 Grade 10 Galois paper. A tangent to a circle is a line or line segment that touches the circle in exactly one place and would not touch the circle again, even if extended infinitely in both directions. I think that's a fine way to define tangent. When a tangent to a curve with center O touches the circle at P, radius OP is perpendicular to the tangent. This is a common circle fact, and I've noticed they've been doing this in the 2017s, because I did the Friar a little while ago. They are giving us common, what should be common knowledge, but circle results aren't really done in high school anymore, so they feel the need to give this information to us freely, when I think part of doing contests is that you should already know this stuff about tangents and circles. Anyway, okay, we got 3 parts to this question, 2 of them written, 1 light bulby. Alright, in the diagram, O is the center of the circle with radius 18, QR is tangent to the circle at P, line segment OQ intersects the circle at S, determine the length of SQ. Okay, and although they didn't tell us here, we do seem to have a 24 here. PQ is 24. So we'll copy our diagram down. There we go. Connect it up. We have a right angle here. P, Q, S. Now, we also have, I guess, R and O. Now, we've got 2 radii here, and we are told the radius is 18. Okay, both radii are 18. So SQ is just OQ minus OS, which is OQ minus 18. So if I just knew what OQ was, we'd be all set. But we have a right angle, so by Pythagoras, we know that OQ squared is OP squared plus PQ squared, and that's 18 squared plus 24 squared. That's going to be 324 plus 576, which gives us a total of 900. So OQ is just the square root of that, which is 30, and that tells me that SQ is 30 minus 18, or 12. All right. Very quick. If we wanted to, we could just write in 12 in the box they provide in the answer booklet, but we do have some justification. Pythagoras, we make the note of how to calculate SQ, that sort of stuff, and that's good. That's good. All right, so we got B and C here. B, a circle is said to be inscribed in a quadrilateral if each side of the quadrilateral is tangent to the circle. Okay, another excellent, very nice definition. A circle with center O is inscribed in quadrilateral A, B, C, D, touching at E, F, G, and H, as shown. If the radius of the circle is 12, OB is 15. Okay, we don't actually have OB written into the picture. OC is 20, and BAD is equal to angle ADC, which is equal to 90 degrees, so we got 2 right angles here. What is the perimeter of quadrilateral ABCD? All right, well, again, we'll copy down a picture. I don't think I have enough room left on this page, so we'll flip the page. And we'll draw our circle first. That's an okay circle. But that tangent line is not, because it's not actually tangent. Well, we'll draw from the circle and thicken it up as need be. There we go. There we go. So what have we got? We've got O here in the center, and then we connect up to all these points. And what did they tell us? We have right angles here. Okay. Right angle there, and it went A, B, C, D, E, F, G, H. Okay. So that's everything that they have told us. We have some 12s. And what else have we got? We've got OC is 20 and OB is 15. Okay, so one thing I'm noticing here is I've got some right angles. BEO is right angle. So let's make some observations. So A, HEO, and HDGO are rectangles because three angles, remember we have to write everything up, so three angles are 90 degrees, therefore other angle is 90 degrees as well. Some of the angles inside a convex quadrilateral, actually I think in any quadrilateral, is 360 degrees. So 390s is 270. That leaves only 90 for the other one. So that's something new. We'll put that in green. We have learned that. Now, because we have radii for all the side lengths, we can actually say that these are not just rectangles, they are squares. So OH is the same as OG, which is OE, which is 12. Therefore, they are squares. And that tells me that AE is AH, is HD, is DG, and they're also all 12. Okay? So what we're going to do is we are going to compute the perimeter, but doing it piece by piece. So AH plus AE plus EB plus BF. We're just going to add them up piecewise. So we have 4 of them already done. We just need GC, CF, FB, and EB. So I'll make some more observations. Notice OEB, OBF, OCF, OCG are right triangles. That tells me that EB is one of the lengths I want. EB squared is OB squared minus OE squared, which is 15 squared minus 12 squared. BF squared is OB squared minus OF squared, which is again 15 squared minus 12 squared. CF squared and CG squared, they are done in a similar manner. We write them all out at once. Minus OF squared minus OG squared, 20 squared minus 12 squared. And that's going to be 9 squared, 9 squared, 16 squared, 16 squared. So that tells me, therefore, EB is 9, BF is 9, FC is 16, CG is 16 as well, and that gets me all the lengths there. So the perimeter is AE plus EB, and yes, we do have to write all this out. Plus HA at the end there. And that's going to be 12 plus 9 plus 9 plus 16 plus 16 plus 12 plus 12 plus 12. And we can just put final answer in the box. I'm just going to tally it up by calculator. 12 plus 9 plus 9 plus 16 plus 16 plus 12 plus 12 plus 12. I get a total of 98. Okay. The 9 and the 16, they make 25, so we got 50 right there, plus 4 12s is 48. Okay, that'll make sense. So that gets me the perimeter, and that was what I was asking for, or what they were asking for. What is the perimeter of the quadrilateral? Okay, done. Great, and we justified everything we mentioned. We mentioned Pythagoras, and that we saw the right angles. We mentioned that we proved that they were rectangles, and then went ahead and proved that they were squares, and what that meant for the side lengths that we needed. So we got our marks, we really do. Alright, so let's finish this off with the C part. Circles with centers O and C are inscribed. Hey, remember the definition of inscribed from B part? They're inscribed in squares as shown. The area of the largest square is 289. I know that that's 17 squared. And the area of the smaller square is 49. That's 7 squared. If T, U, and V lie on a straight line, determine the length of OC. Okay. Interesting. So these circles aren't actually tangent to each other, so we can't just figure out the radii and add them up. What can we do? Well, I'll tell you what we can do. We can draw a picture. I could fit the picture in. I'm not sure about how much calculation we need, so I'll flip the page again. I have infinite paper here. It's all electronic. So no trees are dying. I shouldn't have drawn the squares first, but well. Yeah, definitely should have drawn the circles first. Oh well. Alright. Halfway points are where the tangents are going to occur. So we'll just see if we can do the best that we can. Okay, not great, but not terrible either. O, C, and we want this length right here. Okay. Well, as I'm often fond of saying in a question with circles and tangent points, always connect your centers up to every point of tangency. Every point of tangency. You never know which one's actually going to be useful. I mean, eventually you get a sort of a sense of this, but we never know which ones are exactly going to be what we need. So every point of tangency, connect that radius up with the center, and you always get right angles. Now, they told us in this question we get right angles, but it's something I've been saying for quite a long time. And it's something that you should know. Just for, that's kind of close to the black. Let's use a fun color. How about the red? The actual red, not the fake magenta-y red I typically use. Okay, and we'll choose a different color for the radius, the blue. Yeah, the green's fine. That was a misclick, but whatever. Okay, so we connect up all these points of tangency. What are we going to do? How is this going to help us? Well, let's take the blue and extend this fella over a bit. We get another right angles. And we've got, what are these guys? T, U, and V, aren't they? And they'll lie on a line. So, well, I know the total side length here is 7, and this here is 17. And I know I've got a whole bunch of right angles here. Just lousy with right angles everywhere. So by the same sort of reasoning from the last question, we could say, hey, these are all squares, and they all have side lengths in common, so all of these red lengths are going to be 7 over 2. And these are 17 over 2, and these ones over here are going to be 7 over 2. Well, then I've got a rectangle in here. Let this be, I don't know, x and y. XC is the side length of a rectangle here, and we can figure out the side length of that rectangle, and we can also figure out this length here, and then, hey, we've got a nice yellow right angle triangle. Now, you notice I haven't really written anything up, but I have a plan of attack now. I will figure out OC because it's the hypotenuse of OXC. So I'll go back to the thicker or darker black, I guess. Okay. So I'll say something like connect radii to the points of tangency on the squares. We see that these divide each square into 4 smaller congruent rectangles, or congruent squares. I mean, you could start with rectangles and then prove that they have to be squares like we did in the last question, but it doesn't really matter. we just stated as our observation, 4 smaller congruent squares with sides 17 over 2 or 7 over 2, depending on the larger squares. Okay. Let T, U, V, W be the tangent point between T and U, and I don't know, we'll call him X, and I guess this one over here will be Y. And X, the tangent point between U and V. Okay. So now what are we going to do? We draw a CY. So CY is perpendicular to OW, and Y is on OW. That's what we've got there. Then OYC is right angled. Now, we had CYWX is a rectangle. So CY, which was that longer side, CY is going to be equal to WX, which is the same as WU plus UX, which is 17 over 2, plus 7 over 2, which is 24 over 2, which is 12. Very nice. Okay, so CY is 12. OY is OW minus YW, which is equal to OW minus CX, again by right angle, or not because of by right angle, by being a rectangle. These two values are equal for the rectangle. But that's 17 over 2 minus 7 over 2, which is going to be 10 over 2, which is 5. And now we say by Pythagoras, OC squared is OY squared plus YC squared, which is 5 squared plus 12 squared, get the order right. 5 squared plus 12 squared, which is 13 squared. I'm just not going to bother writing it all out. So OC is 13. And that's what we were asked to show. Now, I did a lot of writing because I remembered my diagram, but let's just flip back. CYWX is indeed a rectangle because we have this right angle and this right angle from tangencies, and this right angle from the definition of Y. That forces this one over here to be a right angle. We do have a rectangle there. Okay. But we connected up the tangency, we get the lengths, and we make the observations of the sides. You could go a little more in depth into proving that if you wanted to. I don't think that's necessary. Name appropriate points so you can refer to them in a smart and intelligent and orderly manner so people who are reading it know what's going on and what you're talking about and don't have to constantly refer to diagrams. Y is perpendicular, gets the right angle triangle, gets the rectangle, gets all the lengths, and then OC is the hypotenuse. And there we go. That's it. That's question number 3 on the 2017 Galois. Nothing else, just A, B, and C done. We have one more question to go, and that's going to be question number 4. So I will see you guys in the next video as we wrap up this Galois paper. Thank you so much for watching, and I'll see you next time.